Hello folks, Rashid here. Thank you so much for joining. Previous video we implemented, we created a microarchitecture for all the R-type instructions. Okay, all the R-type instructions are literally all the arithmetic and logical instruction that operate on two inputs, and the two inputs really come from the two register. So we talked rest of the details in the previous video. If you haven't watched, please watch that. But today we want to talk about the ALU used there. Because if you remember, I didn't go into ALU. We just focus on the higher level data flow and control circuitry. But the lot of stuff is happening inside ALU because all these instructions, add, subtract, and or, exclusive or, shifting, comparison for set less than, all that is happening in ALU. So this is the general block diagram again I created based on the different functionality. So this diagram is not an optimized one. Okay, so let's look into this one and we can, let's start talking about this one. So if you look at, there is different functionality. You see on each block is an operation, is a combination of circuits. And it operates on input A and B. It's the same A coming here from source 1 register, source 2 register. So I didn't do all these connections. It will look messy, but wherever I have A, I assume that is connected to this point. Wherever B, it's connected to this point. Okay, so you can take a look. This block is going to add A and B, and the output is available at output. So whenever an input is available and whenever the data is available at the input of these blocks, the data becomes available at the outputs. Now in our initial simulation, it will available right away, but it takes a little bit time from input A and B to go through different operations all the way when the output is available. The propagation delay and through the transistors, through the gates, takes some time. It's not abrupt, okay? But anyway, whenever some value of A and B is available, and this is going to add, this A block is going to subtract them and put the output here. This block is for shift is an A and B. It's shifting A, and the magnitude of shift is in B. So we only need 5 bits of B, even though we have 32 bits available, but only the least significant 5 bits are used because the 32-bit value maximum you can shift by 31, right? 0 to 31. 0 means no shift, is it? But it's 5-bit value there. So then same thing, this one SLT, let me turn down. So shift logical left. Again, we're not looking into operation, how that happened, but you can look into my digital logic design series, and there I have discussed logical shifts and arithmetic shifts. But here what we're not going inside this block, but all we're saying is shifting this by this much. Set less than. Okay, and this is sign number. So it compares this one and this one. If A is less than B, output will be 1. Else output will be 0. So it's a comparison between the two. Again, we're not looking into how we compare. Then set less than unsigned. It expects that both numbers are unsigned. They're not signed numbers. And again, output is 1 if A is less than B. If not, it's 0. And exclusive OR, A and B are bitwise exclusive OR, and the output is here. This one, I did discuss what is the benefit of exclusive OR, and and this is to invert certain bits, to mask out certain bits, to allow certain bits, right? That's what we do. Shift right, logical, and shift rights can be logical because you're shifting right side. It can be logical where more significant place you put zeros, on arithmetic where the sign bit is extended, right? So again, A shift, B is a shift amount. I put here SH amount. and the shifted result is available at the output. Or of the two bitwise 232-bit values is here, and of the two 232-bit values is available here. Now all these outputs are available, so you have to connect them to a gigantic mux, and the control of that mux comes from this ALU op. Remember this, where is it? This one, this guy, this is the control coming, and where is it? I called it ALU control or ALU control here, and here I'm calling it ALU up, but these are same thing. So the value decide which output from here, which input into the mux is propagated eventually to the output here. And eventually this ALU has two 32-bit input and one 32-bit output. You understand that? So this is very combinational heavy circuit there actually. If you look at our microarchitecture so far, a lot of logic, especially if you have add, we later on we will do when we actually go into implementation, how many logic levels are there, and that will be our critical paths through the ALU. Okay, now on the right side here I have how I implemented this in Python. Now things are pretty simple for a lot of those, so let's zoom in. So input A, in Python, keep in mind, as I mentioned before, this is not we don't have a fixed 32-bit number. So it can be pretty large number, could be 64-bit, right? So when input comes A, like input A to the ALU, this is ALU block, okay? It has input A and output B, and this has a control ALU op. Okay, we are masking here. And if you remember, I told you why we do the masking. Because we want to keep only the 32 bits, because our inputs are 32-bit. We only want to keep those one. If you look at these are 8 character, this is hexadecimal, so each one is 4-bit. So total 32 bits, which are ANDed with this one. So rest of the bits will be 0. Even though A actually is not a 32-bit. Okay, it's much more than that depending on the architecture you have. You understand this, why we are doing this? And we look into this before as well. So, and the same thing, shift amount is only 5 bits. So 1 is 0001, so only 1 bit, and the 4-bit here, 5-bit. Okay, result is going to be a return 1. So if you look at same, modeling in Python is simple. So all I do is ALU underscore op equal to 0, just A plus B put into the result. And eventually I will take the result out only, and I will mask it with 32 bits again. I want to make sure only 32-bit are valid values. Rest of the ones are set to 0. Okay, so simple 0, 1, subtract 2, shift left. So it's going to shift this one by this amount. Okay, this amount we already took from the B. Okay. Now here comes a little complicated, and this is what I plan to explain. So set less than, and this expects a sign number. This is sign 1. So in this one, I created a temporary sign A and sign B, and I did this A minus this if A is larger than this one. And later on we'll shift right. This one arithmetic has something similar. So I want to explain you this concept, and that's it then. All right, so if you look at, let's say A has minus 1, B is plus 1. So if we have 32-bit fixed number in hardware, and our registers and our inputs are only 32-bit, there isn't any other bits there. And then we have hardware that can manipulate that most significant bit as if it's 1, it knows that it's negative. Then what will happen is when these values comes in, this is minus, yes. So always remember that if it's a sign number and all of them are 1s, this one becomes the most negative -1. These are +1, and when you add up all of them, it becomes -1. It doesn't matter what is the length of it. If it's just 16-bit, if all F's is a sign number, it's -1. So A, if this number value comes, we understand it to be -1, and the 1 comes is straightforward, R0, 1 comes here. And then comparison done inside, A is less than B, that is true, so output is set to 1. Okay, so when you have a fixed hardware, this is how we're gonna have, no problem. But in Python modeling, it can be a lot more bits. Okay, so 32, this value is something like this, because we have masked other bit to 0. Remember, we were masking with AND. So we are only keeping 32 bits and we put this one. Now this is less of them is 0. So if we do a comparison in Python, this becomes like a large positive number. This is A. So if this is A, hold on. So you look at it, this number, this is 32 bits. So the largest positive number you can have is 2 raised to the power 32 minus 1. Okay, I always look into this. Well, have a look at this. 4 bits. You will have number plus 7 to -8. These are 16 numbers because this is a sign number, right? So the most significant bit is 1. That is the most negative, -8. And if this is 0, rest of them are 1, this becomes plus 7. So the formula you from here calculate is, this is 2 raised to power 3 minus 1. This is actually this. Okay, the most negative is minus 2 raised to power 3. So if you have n, this was 4 bits, we use 3 here. So if it's n bits, we say most negative is minus 2 raised to power n minus 1, and the most positive 2 raised to power n is minus 1 minus 1. This is helpful because then you don't have to manually calculate those one. You know, it's 32 bits. The most positive number is 2, 3 minus 1. This is our this one. All right. So what happens is if we don't do any conversion, if we look at A, it's actually a huge positive number. B is 1, which is easy. So then A less than B, it's not going to be true. It's going to be false because A is definitely not less than B. So the solution for that is that if A, this number A, is greater than this, why? Because look at F. So this is the largest positive number, right? Greater than this means you have F, that becomes a negative, right? So once you have a number greater than this, then we know it's going to be a negative number. We have to do what? We basically have to, this is the number. We have to subtract it minus 2 raised to the power 32. So if you look at it, take your time and do this actually. Okay, when it's greater than that, what you do is from that number, whatever that number is, in our case, this is the number, you do minus whatever the 2 raised to the power 32. And that will give you now minus 1. You understand that, right? The largest one is when you have 1 and all 0, which is this number, right? So in that case, you're subtracting from the next biggest number, so you get minus 1. So this is a way I have used in Python in order to create a temporary number here. Since I'm comparing the two numbers, if A is greater than this, then I do A minus that large number, 2 raised to the power 32. And if it's right? 2 raised to the power 32. Minus 6, so this is 32 minus 1. The most negative number is minus 3. Yeah, this one is 1 bigger than this, right? You understand that? So this number, the most positive, I think this one is assumed that all these are, this is part of the bigger number. So your n is probably not making sense here. But if you have all these f's, this is like, you have 32-bit, right? And basically it is 33-bit because I'm saying that all these are positive except the one bit there. I hope that makes sense. So this number is one bigger than this, the 295, 296. You can AI this one, is probably better explanation than I did. But hope really you got the point. So if you do that subtraction, and then your values will come out correct. I will think about again. I feel like I probably didn't explain that well. I probably confused you guys over here. Let me rethink again. Okay, and if you have not understood, put that in the comments, please. And I'll think again, maybe in the next video when I start on it. In the first 5 minutes, I will explain you this in a little better way. But you understand this, that look at these numbers. Okay, this is this number. Okay, this is the actual number. So A dash is A minus 2 raised to power 32. That's what you need to remember. You need to subtract. Then you get your whatever actual, if it's a sign number. So maybe that's an easy way to think of that. Okay, whatever number comes with 32 bit minus 2 raised to power 32 bit. And that is this, and that's the actual number we get. All right, I'll finish it here. And I will see you in the next video with implementation for I-type instructions. All right. Thanks. See you. Bye.